Hello and welcome back to Teach Me in 10. In this episode, we're talking to Dr. Anthony Doran, Associate Director of Bioinformatics Field Applications at Oxford Nanopore Technologies. Anthony will tackle common myths in sequencing data analysis and show how recent advantages are transforming the field. Hi, Anthony. Great to meet you, and thanks for joining us today.
Excellent. No, it's great to meet you, and thanks for the opportunity to come and speak today.
So, to begin, it'd be great to talk about how there's a perception that sequencing requires expensive hardware or specialist infrastructure. Is that still the case?
Yeah, for sure. For a long time, that was the case. But one of the things that's really changed over the last couple of years is compute and algorithms gotten better and gotten more efficient, and that definitely helps. But also, one of the things working with Nanopore that we're really happy and really proud about is that we can scale your computational needs to the amount of sequencing you're doing. If you're low throughput or have a small number of samples, you don't need to buy a huge amount of compute or a big massive sequencer. You can buy one of our smaller devices like a MinION. If you are doing a huge amount of compute, like hundreds or thousands of samples, then of course the computational requirements for analysis will increase. But that's one of those things that you can kind of manage depending on your needs. In the past as well, you probably would have needed to do a lot of intermediate processing, and that would add computational kind of requirements and infrastructure needs. But with our devices, we include a huge amount of compute already built into the devices for that intermediate processing. So for sure, that's something that's already included on the device and doesn't add an additional extra cost. But of course, coming back to depending on what you're interested in, that will help define and kind of indicate what your compute and storage needs be.
And sequencing data is often thought to be huge and difficult to manage. Is that really true?
It depends, right? I would say, to be honest, nowadays, no, to an extent. Of course, if you're generating huge amounts of data or sequencing a large number of samples, that will, of course, introduce its own challenges just simply around scale. But nowadays, the file formats that exist and that we generate, for example, are industry standard, have been around for a long time, and importantly, are designed in a way to be efficient for both storage and also access to that data. So for example, without going too much into file formats, we generate the BAM file format, which is a kind of standard format for storing reads, sequencing reads, and information related to those reads, like positions in the genome, or with nanopore sequencing, methylation information we store. And I have to admit, as a bioinformatician, I love the BAM format. It's really well designed to store all of that information super efficiently and much more efficiently than maybe older file formats like the FASTQ format, which has been great, but is really less optimized for that efficient management of data. So, of course, the question is a matter of scale, but the actual files themselves and at per sample level has become incredibly efficient over the last couple of years, which is really nice.
Amazing, thank you. And in the past, sequencing analysis tools were seen as limited or hard to use. How would you describe the landscape today?
Yeah, to be honest, in the past, they absolutely were. It's why I became a bioinformatician and had time as a bioinformatician, because there was really a gap and a difficulty working with sequencing data in the past. But over the last number of years, as technologies and sequencing in general has matured and become more widely adopted, more and more bioinformatics pipelines now exist, but also pipelines designed for users that are not bioinformaticians. I think that's the key difference, right? In the past, people would design software that other bioinformaticians could use. But, for example, we've developed the Epitome solution now, which is a point and click user interface to access bioinformatics pipelines. And what's really nice about that is that they're the exact same pipelines that you could use in the command line or that bioinformaticians will use, but you can access them through a point and click user interface. So not only does it improve the accessibility to bioinformatics, but it also, to an extent, helps free up time within your team because you don't need to spend a lot of time developing those pipelines. Of course, you will still have people to do that, but a lot of that now can be automated through those point and click user-friendly interfaces. And again, I think that's a really nice shift over the last couple of years when it comes to bioinformatics being more friendly to the wider scientific community.
Yeah, absolutely. And we know that sequencing can generate a lot of data. How difficult is this to scale to large cohort studies?
Yeah, that's an excellent question. Because, certainly in the past, doing a small number of samples was always really achievable and really exciting. But, as genomics has become more accessible, we've really seen the advent of these large-scale sequencing projects, and they come with different kinds of challenges, right, around infrastructure and automation, and really how to efficiently process that data. But that is absolutely something that certainly we as a company have dedicated a lot of time to, is developing these pipelines in a user-friendly, well-documented, and really optimized and efficient format. And we've seen that with some of the projects that we've worked on, where we've projects where we're sequencing 50,000 genomes alongside other collaborators and other institutes. In one case, we've over 100,000 genomes on a single project. And 10 years ago, I think that would have been incredibly challenging and maybe not even possible for any technology at that scale, or at least very difficult. But that's something that now we can see we're regularly able to do, and that's all provided with those scalable and kind of efficient formats, well optimized computer analysis, and those pipelines as well.
So, accuracy is one of the most talked about aspects of sequencing. How should people think about it today?
Yeah, that's also a really good question because, in the past, probably people mostly relied on stuff like Q-scores, which are essentially kind of a measure of error probability. But as we've learned more about like reference genomes and genomics in general, really, I think the way in which we should think about accuracy has evolved. So, for example, over the last number of years, we've seen a couple of papers highlighting regions of the genome that are invisible to shorter read technology, for example, or legacy technologies, or even just other technologies like arrays that don't even look at certain regions of the genome. So, if you want to think about accuracy, you kind of have to ask yourself the question, well, how much of the genome are you actually capturing? And if you're generating accuracy metrics based on that, are they reflective of what you can detect? And the Q-score in isolation doesn't really answer that question. It doesn't answer the question like, what can you expect from your data, or how many variants are you going to detect? And there's a really nice example that I always come back to that highlights kind of the value of nanopore sequencing in a single go, where we generate these long reads, right? And they can map to these complex regions of the genome that allow us to identify structural variants or large deletions, for example. But because they're really long, it also allows us to be able to phase them and to separate the alleles and to be able to look at different haplotypes. And that in itself then allows us to look at really complex events like heterozygous events or nested events or compound heterozygosity. So for example, where we might have a small SNP or an indel that occurs in a region that's deleted on the other haplotype. And that's really difficult to resolve with shorter read technology, but that's something that we can do, is to get to that haplotype specific level. And what's really nice as well, that adds to that extra layer of kind of resolution and thinking about, what it is you actually want to get from this data, is that with nanopore sequencing, you also get methylation included in this without doing any other library preps or anything like that at all. And I have a slide there, and you can see on the slide we have this representation of reads at different haplotypes, and there's these two bars at the top where we see like these two tracks demonstrating methylation. And what it's showing us are haplotype-specific methylation, and what we can see is that we have this region that's methylated in one haplotype, but because there's a deletion in the other haplotype, there's no methylation. So what we have is disruption of a methylated region, potentially a regulatory region, And again, that's something that would be invisible to short read technology. So when we think about accuracy, really what I would come back to is, accuracy is Q-score is sure one way, but probably given the improvements in detection and model-based approaches, maybe not the best way to think about performance, or at least not in isolation.
Amazing, thank you. And then to wrap up, as I think we're just about running out of time, sequencing technology has evolved rapidly over the last decade. How do researchers keep up without disrupting their day-to-day work?
Yeah, genomics is a field that is notorious for moving quickly, certainly bioinformatics. But that's one of the things that certainly within Nanopore as a company that we've really like appreciated this. So one of the things that we've done as a company is really define these end-to-end protocols where we provide guidance on, say, the sample prep, sequencing, and the analysis. And it's not just about providing that guidance. What we also do is we lock down on specific versions of the software and the pipelines, especially for those large scale projects, right? If I'm working on 50,000 genomes, that might be a multi-year project. I need to lock down on versions, and we don't force upgrades. We don't force software updates. We provide the user the option to update. So even though there might be the opportunity to maybe update and get access to the newest algorithms or the newest approaches, we also want to ensure that we're supporting consistency and reproducibility in those project life cycles or in those project stages. What's also, just as a quick aside, what's really interesting and really nice about it is that with the way the technology works, fundamentally the technology doesn't change between iterations. And this allows for really exciting things where we have this targeted sequencing approach called adaptive sampling. So this is targeted enrichment of particular regions of genome. But because it's based on mapping reads against the genome, it also means if we want to add new sites, we don't need to revalidate, unlike, for example, if I was using a primer-based approach where you need to validate those primers and go through iterations of that validation. With this, because it's alignment and the technology is fundamentally the same, it means that we can just pull up the new targets file, run adaptive sampling, and the expectations will be the same. So again, the technology itself fundamentally supports the idea of stability within certain contexts, of course.
Amazing, thank you. That's about all we have time for, but thank you so much for joining us today, Anthony. It's been great talking to you.
Yeah, thanks very much. I really enjoyed that. Have a nice day.
Thank you for joining us for this episode of Teach Me in 10, brought to you by Oxford Nanopore Technologies. Oxford Nanopore develops fast, accessible, and easy to use DNA and RNA sequencing solutions that empower researchers across genomics, molecular diagnostics, and bioinformatics. To learn more about their sequencing and analysis tools, check out the links in the description. If you enjoyed this episode, don't forget to like and subscribe, and stay tuned for more insights from leaders in life sciences.